Hello. Today we'll be speaking about our control device project. I'm Andrew Kulababa. Next speaking will be Brian Desjardins. And finally, to finish us up, it will be Jackson Lipka. So our problem statement that was provided to us was flue gas exits a power plant at a rate of 3.4 times 10 to the sixth meters cubed per hour. This is under standard conditions, so 298 degrees Kelvin and a pressure of 1 atm. The untreated exhaust contains 800 parts per million by volume of NOx, and to comply with the new source performance, a control device achieving at least 80% removal must be installed. So we were challenged with figuring out this control device and calculating to make sure that it will be 80% efficient. So flue gas is sometimes called exhaust gas or stack gas, and this is simply gas that is emitted from these power plants due to combustion. So for this, we initially determined our stakeholders. We have a few stakeholders, first being the power plant itself. They need to ensure that they meet these requirements because they don't want to be fined or have any penalties against them. The next is going to be the EPA. They need to make sure that each of the plants set standards, as well as they're always keeping track of the best control devices. So they're always updating their list and changing things. So they need to understand what's going on and what's ideal. Next, we have people breathing the plant fumes. So this is going to be surrounding communities, the employees themselves, anyone downwind. These NOx can cause a significant health impact, as well as just overall poor air quality. And the final stakeholder we have listed is other power plant companies. So, these companies want to be competitive and be as efficient as possible and remove as much emissions as they can. So them understanding the different technologies and what is ideal is pretty beneficial for them. So the technological importance. So NOx can have many harmful impacts for overall air quality. So it can react with ammonia, volatile organic compounds, and other compounds to form PM 2.5 pollutants. So these pollutants easily penetrate into sensitive and deep portions of our lung tissue, which can cause respiratory diseases such as emphysema or bronchitis. NOx can also react to form smog and even acid rain. So NO2 can actually injure vegetation, including trees, forest, and crops. NO2 can also contribute to a reduction in visibility, both directly by selectively absorbing the shorter blue waves in visible light, as well as indirectly by contributing to the formation of nitrate aerosol haze, which decreases visibility. So we need to look into different kinds of control technologies. So here we have listed 4 that we considered. First being low NOx burners, second being reburning, third being combustion staging, and fourth being selective catalytic reduction. So to determine which one of these we wanted to use, we considered things such as cost, ease of installation, maintenance, and overall efficiency, obviously. We had the option to either choose one if it fit all of them categories, or use a combination of multiple to achieve the 80% reduction that we needed. I'm going to turn it over to Brian to talk more on these technologies.
Our first technology we considered was the low NOx burner. Shown here on the right, the top right figure is what one might look like in a coal-fired power plant. Below that is an example of one would have different stages that can be used for a certain application. A low NOx burner provides a stable flame that has several different zones, and these zones can be modified as needed to fit the application it needs. For example, the first zone can be primary combustion. The second zone could be fuel reburning with fuel added to chemically reduce NOx. The third zone can be the final combustion in low excess air to limit the temperature. Like I said, there are many variations on the low NOx burner theme of reducing NOx, and the low NOx burner can produce up to 80% removal efficiency. This can be one of the least expensive pollution prevention technologies with a relatively high removal efficiency. Our next consideration was reburning. Reburning is the recirculation of cooled flue gas with added fuel. This added fuel could be natural gas, pulverized coal, or even oil spray. And this causes the dilution of calories and primary combustion temperature to be lowered. Also, when added as a secondary combustion stage, the presence of added fuel chemically reduces newly generated NOx to molecular nitrogen. Added fuel is only partially consumed in reducing NOx, and burning is completed in a later stage using either combustion air nozzles or over-fire air. This technique has been demonstrated to be effective with residence times from 0.2 seconds to 1.2 seconds and has achieved up to a 76% removal efficiency. Shown here on the right is a figure of a typical gas reburning installation on a wall-fired boiler, so maybe not something we would use at our power plant, but just an example of the versatility that reburning can have as well. Combustion staging was our next consideration. This is the staging of combustion using fuel instead of air. Fuel is divided into two streams here. The first stream feeds primary combustion that operates in reducing fuel to air ratio. The second stream is injected downstream of primary combustion, causing the net fuel to air ratio to be only slightly oxidized. Excess fuel in primary combustion dilutes heat to reduce temperature. The second stream oxidizes the fuel while reducing NOx to N2. This is going to achieve a little bit of a lower removal efficiency than the devices that we've discussed previously. So this might be something we consider if staging more than one control device is something we would want to do. An example is shown here to the right of how this might work. Our final choice is going to be selective catalytic reduction. Selective catalytic reduction systems usually use ammonia to selectively reduce NOx to N2. Ammonia, usually diluted with air or steam, is injected through a grid system into the flue gas stream upstream of a catalyst bed. And this catalyst bed could be made of vanadium, titanium, or platinum based. And this is enclosed in a reactor. On the catalyst surface, the ammonia reacts with nitrogen oxide, NO, to form molecular nitrogen and water. The reaction of ammonia and NO is favored by the presence of excess oxygen. The primary variable affecting NO reduction is temperature. A given catalyst exhibits optimum performance within a temperature range of plus or minus about 28 degrees Celsius for applications where flue gas oxygen concentrations are greater than 1%. Below this optimum range, the catalyst activity is greatly reduced, allowing unreacted ammonia to slip through. Above the range, ammonia begins to oxidize to form additional NO. Further, excessive temperatures may damage the catalysts. Now, this can achieve a removal efficiency of up to 90%. And higher reductions are possible, but generally are not very cost effective. Seen below is a small diagram of how one of these systems might work. Next, I'll hand it off to Jackson to discuss our choices further.
So for our final system, we decided to go with the selective catalytic reduction system. This was chosen, as it had the ability to achieve a reduction efficiency of not only the 80% we needed, but it could go up to 90%, whereas the other ones, such as the combustion staging, could only reach 50%. As well as when we chose the selective catalytic reduction system, it will not impact the efficiency of the power plant or the construction. As such, with other methods, they would require things like staging, such as the low NOx burners, which got close to the efficiency we needed. It got to 80%, but that was the maximum that it could get to. So it was more likely for the selective catalytic reduction system to get to that 80% that we needed. Also, when we would have to install the other methods, such as the combustion staging or the low NOx burner, they would be a lot more complex and their costs would be much higher. So they would cost the power plant more, or whoever is paying, and actually building them inside the plant would be much more complex, require a lot more work, and most likely take a lot more time. So to find the NOx removal efficiency that we needed, we have the design equations above. Now, there was a lot of things that went into trying to figure out what equation we actually needed to find our NOx removal, but the main one that we found was that when using a selective catalytic reduction system, removal efficiency will actually change with catalyst activation. So because that is the case, we have to therefore obviously put the catalyst into the equations and how it changes, because the catalyst will change over time. So as can be seen above, we have our SFR, which is our ratio of moles injected into the system by the moles of NOx removed. We have our K catalyst, which is just a constant for our catalyst activity. This is what will show our change over time and why we had to use this equation. Our A specific, which is the specific surface area of the catalyst, which would then be later divided by the catalyst volume, which can be seen all the way on the bottom of our slide with the VOL catalyst. And then finally, our V space, which is the volumetric flow rate of flue gas divided by the catalyst volume. That equation can be seen in the top right. So when doing our equation, we had to find a few assumptions, as we could not find everything. First, we had to assume our K catalyst value. We decided to go with a value of 20. This was found from GraphPad. We also had to assume our V catalyst of 6,000 meters cubed. We were able to get that from the website, from the Nuclear Energy Institute website. We had to also assume our surface area of the catalyst to then later find our A surface. We found that through the American Nuclear Society. And finally, we had to find an average for our SRF value, which we then got from the Nuclear Regulatory Commission, so all websites that are very credible. As can be seen above, we have our calculated efficiencies. So our V space we found when we took our flue gas that was given in the original statement, the 2 times 10 to the 6th, and divided it by our volume of catalyst, which when converted from what we had before, the 6,000 meters cubed that we had gotten, it was then changed to 211,888 feet, giving us a V space of 9.44 minutes. Our A specific was then just using our volume of catalyst before from our assumed value that we got for our surface area of the catalyst, which would again later give us a 0.051 feet squared per feet cubed. Finally, we were able to use these values to get our NOx burner efficiency. Sorry, not NOx burner efficiency, our NOx removal efficiency. When all of those numbers were finally plugged in with our SRF of 0.925, we were able to achieve a removal efficiency of 81.3%. Now, to come back to our unique aspects of our problem and the summary of the total. Again, our problem was we had a power plant which had an emission of flue gas of 3.4 times 10 to the 6 meters cubed per hour. This was under standard conditions. Our exhaust was an untreated NOx exhaust concentration of 800 ppmv. Finally, we were tasked with removing 80% of the NOx, which thankfully, using the selective catalytic reduction system, we were able to remove 81.3%, just getting over the range we needed to meet standard of the NOx removal. Thank you.